introduction, Chairman. Good afternoon, ladies and gentlemen. Welcome to Merck Science Connect in IMID 2024. My name is Junho Kim, and I'm leading OLED material development and research in Merck Korea. Today, on behalf of all our experts in Merck, I will share what we as Merck have investigated and developed display materials for automotive applications. So we wanted the drivers and passengers can see things as clear and sharp as in reality on our screens, regardless of viewing angle and light conditions. On top of that, we believe the display can be very thin and having the superb qualities. We have our portfolio in liquid crystal and OLED. So both technologies are already used in automotive display application, but we believe still we can open unrivaled design, a new opportunity of display in the future.
Yeah, Dr. Kim, would you please screen?
Oh, yeah, this one first. Sorry. This one first. Okay, with these two technologies, is not only located in front of drivers or in front of the front seat, I mean the CID position. It can be integrated onto the dashboard or seats or even doors. And because of this free form factor and possibly large screen size, we can reduce the number of displays in a car. From now on, I will talk about three technologies which are liquid crystal and OLED as a display, and the ALD precursor for thin film encapsulation for OLED stack. First topic is liquid crystal. We are also developing so-called LC window, die-doped LC for sunroof or rear window, but it is not a display application, so I will skip it. So we have two focus areas, which is head-up display and the CID or clusters. There are a few bullet points for head-up display, HUD. We need high TNI, which is LC clearing point, which still the temperature which the LCD can operate. So because the HUD located just under the front windows, the temperature goes much higher than other displays in a car. So we are developing the LC with high TNI. And for cluster or CID, obviously we need high contrast ratio and also fast response time and reliable LC with various temperature for clear picture. So we offer a clear vision for automotive displays wherever you drive. We enable outstanding contrast displays toward 1,500 to 1 or even beyond, thanks to our UBFFS mode. We also pushing switching speed beyond the limit to enable your display response swiftly to your command. And we are also, as I said before, we are also developing the LC which can operate within various temperatures from -40 to plus 115 degrees Celsius. And this operating temperature still we fulfill the response time and fulfill the spec of the OEM 5.1. this is our, sorry again. So cutting edge LC single, so-called LC 2020-1, giving us a remarkable response time and also the contrast ratio. The K average is the key parameter representing contrast. And compared to the reference, if we are using this LC 2020-1 in a mixture, then you can improve the contrast ratio at the same response time, around 10%, or you can faster the switching time, more than 10% with the same K average value. Another example is LC19-3, our latest LC mixtures, LC singles. So it gives you really high operating conditions. Its TNI goes up to 115 degrees C, and actually the bar chart on your right-hand side, the mixture D having the 10% of LC19-3 already commercially used. Based on that mixture D, even if you increase this portion of LC19-3, 15 to 20%, still this stability stays same. So I just introduced two examples of liquid crystal. I now move to OLED. We have currently the broad portfolio mainly in common layers and also emitting layers. In common layers, we have HTMs and electron blocking layers and all the primes and even the host materials in PCGL. And ETL portfolio, we have, of course, ETL and hole blocking layers. Host materials, we are developing both E-type and H-type host, and also we are developing the so-called premixed host. You can evaporate two hosts in one source. So the OLED in automotive is not that big difference. It's not that big different from the display for mobile or TV application. Always OLED requires the higher efficiency, longer lifetime, and lower voltage. We are calling it internally the master triangle. And on top of that, maybe better to close. On top of that, so we are developing deuteration technology. We developed and keep developing deuteration technology to push the lifetime further. And lastly, we are investigating, studying, and developing the materials to fulfill beyond this three master triangle, so which we will show you shortly later on. So this master triangle, the voltage, efficiency, and lifetime are the main requirement for any OLED in any applications. But if you want to have a higher efficiency, then there is always a trade-off of lifetime or voltage because of change of charge balance. But of course, depending on what you are using, you can improve your OLED performance towards lifetime or efficiency with the cost of other parameters loss. But it is one example of our HTM portfolios. In green stack, we compared to the reference HTM1, if you choose one of those three materials, you can go further to lifetime, efficiency, or voltage. So if you have a right combination, the convince you can keep other parameters and also improve the one or two parameters in these three triangles. The duration, as I said, is the beauty of duration is really keep all other parameters same and improving only lifetime. It's now widely studied and published a lot in the papers. So really, the duration is heavily or actively used from emitter to host and also the blocking layers. So here you can see, depends on what kind of materials or combinations you use, then you can really improve the lifetime tremendously. So next dimension, as I said, these three parameters are basic, but there are more requirements or needs came and comes. So, for example, viewing angle is also critical, depends on your application, and also the switching time and crosstalks are crucial for the vivid color. So all these requirements, together with our customers and partners, we are implementing these requirements to our material development. The last topic is ALD precursor. So the demand of the advanced automotive display is continuously growing, especially the touch-capable and also curved displays are kind of main driving force these days. And TFE, thin film encapsulation, is used mainly for the encapsulation of plastic OLED, flexible OLED. But for this car application, also we are using these ALD processes. So there are many methods to deposit these thin films, organic, inorganic, especially inorganic films. But among them, the ALD is considered as the best solution in many aspects. For example, the thickness control, composition control, and also uniformity, etc. There is an example of our product, VM6533. So with the relatively low process conditions and the process powers, you can really control the thickness of the film, and also there is a very low impurity of carbon and nitrogen. Here, zero doesn't mean the absolute zero number in number. It means under the detection limit, and typical detection limit is 1%. That shows the really uniformity or uniform film formation or conformality of our ALD precursors. So wherever you see the thickness of the film are almost same, and you don't have the void or the fields. So that is the beauty of our ALD precursor and ALD processes. So we have two groups of precursors, not only for ALD, but also for other deposition method. One is organoline groups, and the other one is organometallics. So we have a broad portfolio of the precursors. So Merck is your trustworthy partner to really open or realize the unprecedented display design innovations. That is my last page, but I have two more advertisement actually. First one, in IMID we have 2 topics in OLED, 2 invited speakers. One is for, about duration, but actually it's the same time to this session. So maybe you can refer on the abstract or papers. But tomorrow we have another presentation about the crosstalk or lateral current of OLED. So if you are interested, please join the session as well. Thank you very much.